I'm Tim. This PCB Sync.
When designing base station antennas, antenna arrays, and other wireless infrastructure, in addition to DK and DF, there's another very important parameter, PIM, which stands for Passive Intermodulation. The RO4334, part of Rogers' RO4534 series, is a high-performance, cost-effective, high-frequency laminate specifically designed for the antenna market. It is a ceramic-filled glass fiber-reinforced carbon fiber composite material. Its main features are controlled decay, low loss, excellent dimensional stability, and low PIM performance. Let's first take a look at the most important electrical parameters of the RO4534. Its process decay is 3.4 with a tolerance of plus or minus 0.08. When used for antenna size, transmission lines, and electromagnetic simulation, the design reference constant is 3.55. In terms of loss factor at 25 GHz, its typical loss factor is 0.0027, and at 10 GHz it is also 0.0027. Decay affects impedance, propagation speed, and electrical length, but in practice it is also related to dielectric thickness, line width, copper thickness, and the structure of the transmission line. The lower the DF, the smaller the dielectric loss usually is, but the final loss is also affected by copper foil surface treatment and processing quality. Compared to general purpose high frequency materials, a very important feature of RO4453F is its low PIM. Antenna applications, PIM, which stands for Passive Intermodulation. When multiple high-power RF signals pass through connectors, copper foil, surface treatments, or other non-linear contact points, new intermodulation signals may be generated. If these spurious signals fall into the receiving frequency band, they will affect the system's sensitivity. Rogers' product page also lists the typical PIM value for RO4534 as minus 157 dBc. However, PIM is not determined solely by the substrate. Factors such as copper foil type, current density, etching quality, surface treatment, and circuit cleanliness all affect the final result. Shown on the screen is an example of a 4-element patch antenna array and its feed structure. The 4 patch elements should be kept as uniform in size as possible, and the feed network should also remain symmetrical. The size of the patch mainly affects the resonant frequency. The width of the feed line affects the impedance, and the length of the feed line influences the phase relationship between each element. If the material's decay, board thickness, or trace width changes, then even if the copper trace appears identical in shape, the actual impedance, electrical length, and phase will also change. For antenna arrays, these changes not only affect return loss, but may also impact the amplitude and phase consistency between elements and the final radiation pattern. Therefore, when switching the original antenna design to use RO4534, at the very least, you need to reconfirm the trace dimensions, feed line impedance, feed line routing, and element spacing, and then readjust them through electromagnetic simulation and physical prototypes. The coefficients of thermal expansion, CTE, of RO4334 in the X, Y, and Z directions are 11, 14, and 46 parts per million per degree Celsius respectively. Its thermal conductivity is 0.6 watts per meter Kelvin, and its water absorption rate is 0.06%. The TG, glass transition temperature, of the RO4500 series is all above 280 degrees Celsius, and they also offer excellent dimensional stability. These characteristics help large antenna boards maintain structural stability during processing, installation, and temperature changes. In terms of processing, RO4534 is compatible with conventional FR4 high-frequency, high-temperature, lead-free soldering processes. Compared to traditional PTFE antenna materials, it does not require special metallized through-hole treatments. However, this does not mean that all FR4 processes can be directly applied without modification. Drilling, etching, compensation, copper foil selection, and PIM control still need to be confirmed by the board manufacturer based on the actual stack-up. It should also be noted that RO4534 itself is a non-flame retardant material. If the product explicitly requires UL 94V0, further evaluation of RO4535 or other materials that meet flame retardant requirements is necessary. The most typical application of RO4534 is in cellular infrastructure, base station antennas, and antenna networks. Its advantage does not lie in pursuing the highest DK or the lowest DF, but rather in achieving a balance among the low PIM required by antennas, controlled DK, dimensional stability, ease of processing, and cost. If you are designing an RO4534 antenna PCB, PCB CELEC can assist with material recommendations, interlayer evaluation, impedance calculation, PIM-related DF review, prototyping, and mass production. Scan the QR code in the image and upload your Gerber files to start requesting a quote. If you found this content helpful, please like and subscribe. See you in the next episode.